You're
Hello,
right.
my name is Ilyass Belaribia, and this is my project. It's going to basically talk about Euler and his identity and formula. So first of all, to introduce Euler, his full name is Leonhard Euler. He was born on the 15th of April, 1707, and he died on the 18th of September of 1783. And he's shown in the bottom right corner. He was one of the most influential, important people in math, physics, astronomy, and engineering, amongst other things. He discovered infinitesimal calculus and graph theory, as well as pioneered and led several branches such as analytic number theory and topology. Many of the terms that we use in mathematics and think that are very given or obvious were discovered by him, such as employing the function of y to be interchangeable with f of x, and using sigma to symbolize summation, as well as using I to express the imaginary numbers, the square root of -1, and developing E, also known as Euler's number, which is roughly equal to 2.71828. His contributions are considered some of the greatest of all time, like as we were told by like extremely great scientists such as Pascal, and three of his equations were given a place in the top five most beautiful equations of all time, granting his equation Euler's identity the top one spot, and it's shown in the figure in the middle. Okay, so how we're mainly going to focus, first of all, we're going to focus on finding Euler's formula. And in order to do that, we're going to use the Maclaurin series, which is the Taylor series shown below with A equals 0. We're going to substitute A with 0. It's going to be, and if we expand the Maclaurin series, it can be rewritten as f of x is equal to f of 0 plus the first derivative of f of 0 times x plus the second derivative of f0 times x squared over 2 factorial. And we're going to keep going on and on like that. And the template of it is going to be like the nth derivative of f of 0 times x to the power of n over n factorial. Now, in order to get to our formula, first of all, we're going to substitute f with e to the power of x. And we know that the derivative of e of x is always going to be e of x. It's never going to change no matter how many times you derive it. And we're also going to need to know that f of 0, aka e to the power of 0, is going to be 1. And if we substitute that into the expansion that we gave to the Maclaurin series, we're going to be given e to the power of x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. And we're going to consider this the first equation. One thing we should know also before we get into it is the Maclaurin series of sine of x and also cosine of x. And this is the expansion of the Maclaurin series shown before. So in order to do that, we're going to consider f of x equal to sine of x, and we're going to need to know both the sine of 0, which is equal to 0, as well as the first, second, and third derivative of the sine of 0, which were shown here. The first derivative is going to be equal to 1, second is going to be equal to 0, and the third is going to be equal to -1. And we're going to keep looping this over and over in order to find the equation. It's going to be equivalent to sine of x equals 0 plus 1 times x plus 0 times x squared over 2 factorial plus -1 x cubed over 3 factorial. And you're just going to keep looping back over again like that. And we're going to get in the end sine of x is equal to x minus x cubed over 3 factorial plus x to the power of 5 over 5 factorial minus x to the power of 7 over 7 factorial, and so on. And we mainly here we mainly have x to the power of an odd number like 1, 3, 5, and 7. And we're going to keep that in mind. Next, we're going to find cosine of x. We're going to substitute fx for cosine. So cosine of 0 is going to be 1. And we're going to need to find its first derivative, second derivative, and the third one, which are shown here in front of you, 0, -1, and 0. And we can substitute that into the Maclaurin series that we have, and it's going to give us cosine of x is equal to 1 plus 0 times x plus -1 x squared over 2 factorial plus 1 x squared over x to the power of 4 over 4 factorial, and so on. So cosine cosine of x is going, in the end, it's going to be equal to 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial, and so on. So we can rewrite the first equation as shown in the pink triangle, rectangle, e to the power of x. So what we're gonna do is we're gonna group all the x's that have an even power with each other, and the ones that have an odd power with each other. So we're gonna have 1 plus x squared over 2 factorial with all the ones that have like the power of 2, 4, 6, and so on the first side, and we're going to put the ones that have the power 1, 3, 5, and 7 on the other side. And we're going to put them in parentheses. So first of all, we're gonna substitute x with I of x, which will give us e to the power of I of x. And wherever we see an x, we're gonna put in its stead, we're gonna put I of x. So where there is x squared, we're gonna have ix all squared, all of it squared. And where we have ix, where we have x cubed, we're gonna have ix all to the power of 3. So next, we're going to use the special properties of I squared, which is going to be equal to 1 and minus 1. And if you know how to, and if you took college algebra, I think you would know how to find the I to whatever power you have. So let's say I to the power 4 is going to be I squared times I squared, which is minus 1 times minus 1, and is going to give us 1. And let's say I to the power of 6 is going to be I squared times I squared times I squared, which is 1 minus 1 times minus 1 times minus 1, which is going to be, in the end, equal to minus 1, and so on. And before we apply this property, we have to put, I forgot the word. We have to distribute the powers onto the I and onto the x, so we can see which properties we're going to use and how we're going to do it, as shown in the equation in front of you. So we're going to substitute wherever we see I squared or so, we're going to substitute it, and we're going to have e to the I of x equals to 1 plus minus 1 x squared over 2 factorial plus 1 times x squared over 4 factorial, and it's going to be repeating over and over again. And the second parentheses, we're going to have I of x plus minus 1 ix cubed over 3 factorial plus 1 times ix to the power 5 over 5 factorial, and so on, which in the end will give us this equation in the bottom. Now, this is going to be the second equation. Now, what we can do is we can factor the I out of this equation, like we had I of x minus ix cubed plus ix to the power 5. We're gonna like factor it out and put it outside the parentheses. And now, if you look closely at the first and second term, they're respectively equal to cosine of x and sine of x Maclaurin series expansions that we found before, like as shown here. I'm gonna rewrite them here. So therefore, all we have to do is substitute the first term with cosine of x and the second term with sine of x, in the end, to receive the Euler's formula, which is e to the power of I of x equal to cosine of x plus I sine of x. Next thing we're going to do is try and find Euler's identity. And we're going to do that using basic trigonometry and arithmetic as follows. First, we're going to substitute x with pi. Is going to give us e to the power of I times pi. And we're going to substitute the x inside of cosine with pi and sine with pi. So it's going to give us cosine pi plus I sine of pi. And we know the values of cosine and sine of pi are going to be minus 1. Since pi is here, is going to give us cosine is going to be equal to minus pi, and the sine of pi is going to be equal to 0 here. Now we're going to plug those values into our equation, into our previous equation, and it's going to give us e to the power of I of pi is equal to minus 1 plus I times 0. This is going to be 0, and what we're going to do is we're going to add plus 1 to both sides in order to get our final Euler's identity, which is considered to be one of the most beautiful, as I said before. This equation seemingly connects completely unrelated terms, such as I, which is an irrational number, pi, a number that intrigues scientists throughout history and is mainly used or related to circles, and Euler's number, in a single equation with basic numbers such as 1 and 0. So, in conclusion, I just want to talk about my personal experience, which is our high school professor had already introduced us to Euler's formula, yet I've always wondered where it came from or how to prove it. After doing this project and this research, I realized how much of a great person Euler is, having discovered and invented various terms that we consider to be very obvious and a given, but it was extremely rigorous. This project made me believe that human potential can be limitless, considering all the achievements he had, and how seemingly unrelated things can be found to be interconnected in the most mind boggling, surprising ways. He inspires me to work hard and strive to be someone who is great and others could look up to. So that's it. Thank you. And